Hey Chemistry, Mrs. KJ here, going over 5.01 reaction rates and energy. Chemical reactions take place at different rates. Some reaction systems are slow and may take years, while others occur in a fraction of a second. The rates of individual reactions are determined by the collisions of the reactants and by their speed and orientation, or in other words, what direction they're facing. Many factors will influence reaction rates, such as temperature, concentration, particle size, and catalyst. Equilibrium is also affected by the same types of factors as individual reactions. In this unit, you will learn about the reaction rates and the dynamics of chemical equilibrium. Lesson 1, Reaction Rates and Energy Activation. Atoms, ions, and molecules collide in chemical reactions. The rate or the speed at which systems of these particles react can vary. A system of chemical reaction is very much like a demolition derby. Like the cars, the reactants collide with each other. If they hit at the right speed and orientation, then they will form a product. The speed at which this happens depends on the energy required for the reaction, as well as other factors. You will learn about the collision theory of chemical reactions, how reaction rates of systems are measured, energies of reactions, and factors affecting rates. So, chemical reaction. The time it takes to happen is called the reaction rate. Chemical reactions begin with reactants becoming an activated complex, then becoming products. Goals for this lesson: explain collision theory as it applies to chemical reactions, explain that the reaction rate is expressed as the decrease in concentration of the reactants or the increase in concentration of products per time, interpret a diagram that illustrates reaction rate with time, explain the role of activation energy in chemical reaction. So you can get your student guide from slide 3. And on it, I just kept the beginning part, the unit objectives, the introduction, the goals, and of course, keywords and pronunciation. So activated complex is a temporary arrangement of interacting chemical species that is an intermediate between reactants and products. So in other words, reactants turn into products, but in between that happening, they all kind of bind together in a big mess, and that big mess of them bound together before they rearrange is called the activated complex. We have activation energy. That's the energy barrier that must be overcome for a reaction to occur. Or in other words, you have to have a certain amount of energy for a reaction to happen. Catalyst is a substance present during a reaction that speeds up the reaction, but is not used up or changed during the reaction. Transition state is the state of a system or individual species between reactants and products. So that goes with the activated complex. So it's that middle part. So it's not a reactant, it's not a product, it's the squished big mess in the middle, and that happens during the transition state. Okay, chemical reaction systems are like demolition derbies. In a demolition derby, race cars drive inside a ring and collide with each other. Some cars are going faster than others. When cars collide, they may merely bounce off one another. In other collisions, the cars may interlock and then separate. In the collisions, some cars might lose parts, others might gain parts, such as a bumper, and some parts might scatter around the ring. Chemical reaction systems are much like a demolition derby. Reactants move about at different speeds and run into each other such that they can react and form products. This view of chemical reactions is called collision theory and can explain many things about chemical reactions. Under the picture, in a chemical reaction, molecules collide and either react or do not react. Reacting depends on a variety of factors. Two views of reactants. Notice that when talking about chemical reactions, there are two components. First, there is the chemical species. So chemical species means atoms, ions, molecules, and so forth. And there's the chemical species that makes up the reaction system. Second is the system itself. When reading about reactions, pay attention to which is being talked about. For example, two molecules can react to form a product quickly, but the entire system of reactants can take a long time to form products. Okay, so let's go ahead and add a little bit of review of collision theory to our notes. So I added collision theory. Reactants move about at different speeds and run into each other such that they can react and form products. Reactants collide together in reactions. Molecules are in constant motion. When reactants come together, each reactant is in motion. Some molecules move faster than others. Also, the orientation of molecules change as they move. So in other words, if they're right side up, upside down, sideways, backwards. For a reaction to occur, the reactants must hit each other with a sufficient speed and in proper orientation for the reaction to occur. For example, ethene reacts with hydrochloric acid to form ethyl chloride. In the reaction, a hydrochloric acid molecule attacks the carbon-carbon double bond of the ethene, and the hydrochloric acid splits apart. Hydrogen bonds with one carbon, while chlorine binds with another. However, the HCl molecule must attack the double bond at just the right orientation. Okay, so molecules in a chemical reaction collide but won't react unless they're properly aligned. Move this HCl molecule into position to react. Okay, so right now, if I would let go, it's going to hit over on this side. Okay, and nothing happened. If I let go right here, now it's hitting the hydrogens, nothing's going to happen. If I line it up right here, boom! I had to hit exactly where the double bonds are in order to make it react. So that's what it's talking about orientation. If they hit each other down here, nothing's going to happen. If I hit it over on this side, nothing's going to happen. I have to have the two molecules oriented right. Kind of think of like you have to get the key inside the lock. So you have to line it up just right until boom, it can hit the double bond, break things apart, and make a new molecule. Okay, so I added the atoms/molecules have to be in the right orientation, like a key into a lock right side up, right? The key won't work if it's upside down. And at enough speed for a reaction to occur. Reactants form an activated complex. When the reactants collide with sufficient speed and the proper orientation, they don't immediately form the products. Instead, the reactants interlock, much like two cars colliding in a demolition derby crash. The interlocked reactants form an intermediate species called an activated complex or transition state. The activated complex then breaks apart to form the products. So this is what I was talking about when they come together. They kind of form a big mess in the middle, and then they rearrange and form your products. Consider the reaction of bromomethane, CH3Br, and hydroxide, OH negative, to form methanol and bromine ion. So here we have CH3Br, so that's this, C, here's our C, 3 H's, and our bromine, plus an OH negative molecule. In the transition state, the oxygen of OH forms a partial covalent bond with the carbon of CH3Br. The carbon-bromine bond gets partially broken. Once formed, the transition state breaks into products quickly. An activated complex is the intermediate state that lasts a very short time as the reaction proceeds. Okay, so bump, and now they're all stuck together. This is that big mess I was talking about in the middle. It's called the activated complex. It happens during the transition state. And then they rearrange, and you have your two new molecules. So again, we have reactants come together in the transition state to make the activated complex, break apart into the two new molecules. So we know that reactants form products. Okay, so reactants all bunch together to make one molecule or one big mess. This is called the activated complex during the transition state. Then it breaks apart into products. So instead of just reactants to products, now we're saying, well, there's a little more to it. It's got to form a big glob in the middle and then break apart. So for example, HCl plus NaOH makes this big glob. Very scientific, I know. HCl, NaOH. Then it breaks apart into H2O and NaCl. So the blob, HCl, NaOH, is called the activated complex. When it is happening, that's called the transition state. Okay, so when that is present, it's called the transition state. And then, of course, if we write this out, we don't ever really write out the activated complex in the transition state. Scientists just say, oh yeah, we know that that happened. We just write out the before and the after, and that's it. Activation energy is required for the reaction. We have talked about reactants colliding with sufficient speed to form the activated complex, that big glob in the middle. But what do we mean by sufficient speed? The speed of a molecule is related to the amount of kinetic energy. The graph is an energy diagram for the hydroxide bromomethane reaction. The reactants must have a certain amount of extra energy to form the activated complex or transition state. The energy difference between the activated complex and the reactants is called the activation energy. Activation energy is the energy barrier that must be overcome for a reaction to occur. Okay, so my reactants are just sitting there. They're sitting there, and look, they're getting more and more energy. As we're going up the y-axis, we're increasing energy, and then, oh, I got a lot of energy. Boom! Now I make a transition state, and then, whew, I can relax, releasing that energy, so it's exothermic, releasing energy, and I have my new products. This dotted line right here, this is how much energy they have to start with. They need this extra energy in order to form a transition state, right? Things need energy in order to move, just like you need energy to get up off the couch. The reactants need energy to make the big glob, and then they can break apart into products. The graph is an energy diagram for the hydroxide bromomethane reaction. Only those reactant molecules that have kinetic energy greater than or equal to the activation energy, so they have enough energy, will form the transition state and subsequently become products. So activation energy is required for the reaction to occur. The reactants must have a certain amount of extra energy to form the activated complex or transition state. If they don't, the reaction won't happen. Activation energy is the energy difference between the activated complex and the reactants. So in other words, we started out with this much energy, okay? And so on our graph, it's right here. And then we say, okay, we need this much energy in order to actually make the reaction occur. And then the difference between these two arrows, that's your activation energy. So they could give you numbers. They could say this is 100, this is 150, and then my activation energy would be the difference, or 50. Energy diagrams of chemical reactions have certain features. Carbon monoxide and nitrogen dioxide are produced when gasoline is burned. These two gases can react as you see here. The energy diagram shows that the activation energy, which they abbreviate E for energy, A for activation. The energy diagram shows that the activation energy to form the transition state between the reactants is the difference between the energy of the reactants and the energy of the transition state. So in other words, again, I need energy to go from here up to my big blob or my activated complex in my transition state so they can rearrange and form the products. So EA, the activation energy they're saying in this case, happens to be 134 kilojoules per mole. There is no way you could have told that from this graph. They should have put numbers on here and said like, oh, this number is 100. This number is 234. Then you could see where they subtracted to get that. Notes about this reaction. The energy of reactants is greater than the energy of products, so the reaction is exothermic. We let energy out. The reaction with a large activation energy is less likely to happen because fewer molecules will be moving fast enough or have sufficient energy. The reaction can run in reverse, but the activation energy required to form the transition state from the products is greater. Activation energy reverse equals 360 kilojoules per mole. This is why reactants tend to run primarily in one direction. In other words, you can go backwards, but look, they had to have this much difference to happen forward. To go backwards, they need this much difference in energy, the difference from the product to the transition state. The activation energy for this reaction creates a barrier for the reactions. The higher it is, the less likely that all reactants will become products. So I added note if the activation energy is too high, like my green line, see how much extra energy it would take? Then few reactants will turn into products because so much energy is needed. So sometimes the activation energy is too much for a reaction to happen. Reactions can go backwards, but look how big this purple line is compared to the dotted line. It would take a lot more energy to get up over that hump in order to turn back into the reactants. And I'll finish this lesson in the next video.